Thank you. I wonder how it ran for me then. Okay, I believe you. I totally believe you. So, all right, I can quickly that. All right. Installation of H5Py is.
It's the one that uses, if you're not using
We're not using that part of even what's in the run, what's even in the prep data script. So we don't. You only need it to run the prep data script, but the prep data script, we're not using the H5Py. The fact that the Java and the C++ teams, that their software systems didn't work was surprising to me. I urged in to the session we're going to cover today. But you've got links to like the SciPy Dask tutorial, the PyCon parallel data analysis tutorial, the standard Dask tutorial, and the reference Dask talk. So if you want to like do the summary version of this for your colleagues, give like a lab talk or a tech talk, a meetup talk, you can, after this, you're going to be in a position to basically go to this and give Rockland's talk on parallel programming in Python, but I'm not going to. So if you just navigate, you know what, we're only looking at the flights data. So if you're using Jupyter, whatever Jupyter, or just command line, if you go and look in your data directory, and then you go and look, not flight JSON, if you go and look in NYC flight, what's that? You're just going to follow on the screen. Okay, just going to follow on the screen. All right. The really short version of what the benefits of Dask are. It's the side of the screen there. It's in. There we go. Box parallel data structures with parallel methods. They're Daskified of NumPy array and pandas data frame. At a high level, what we're going to see first to help us like get our introduce, have like a soft Dask, is that Dask has implemented of a whole bunch of independent Dask data frames in independent threads if you're running on a single computer, on independent processes if you want on a single computer, or on independent processes of computers. So that's where like the real extra work. It does lots of like a lot of automatic Dask where you also need it when you want it, when you need it. Okay. So at a high level, this room familiar with NumPy and ND arrays frames. Dask gives us parallel versions of those, and you might think, why parallel version of those? You can imagine that. So you've hit on the chip, this one, looking at, fully say, kind of like make work together. And then you can write methods that can operate on that distributed data so you get parallel action on it. About Dask. All right, now these help people out who are a little bit stuck. So for here, you need fingers to do this. Look at it and think about what the result is going to be. You don't have to think about the results for that. That's just an assignment where you want to think. You want to think, okay, what am I going to get here? What is this actually going to be? Is this going to be like a random with the actual typing returned is? And then you're going to do this operations, and then you're going to see what you get back to that object. And there's a little in here, and like I said, I'm going to then talk through this. I said 10 minutes. I'm going to give you about 5 minutes, and I'm going to see how many people I can help out who have issues other than just slow net. So 5 minutes, run through those. Okay, vectors are a little bit more interesting because 3, so that's actually the row, of course. It interprets that fancy indexing on the Dask array. It knows that the thing it gets back is going to be effectively a vector of length 10. Knows its type, and it knows its chunk size. And we'll come back to the chunk size part a little bit later. That chunk size might be like a bit of a surprise, or you might already have some ideas about what's going on behind the scenes, why the chunk size there is 5, rather than what you might imagine, which would be, why isn't the chunk size 10? If we want to actually get those values back, we call compute. And I'll note here, I think somewhere else I actually illustrate this. This is a NumPy ND array. When we do compute, the thing that's returned is now a NumPy ND array, is what gets handed back to us. We can do a region or matrix. Here, we know the shape, we know the type, we know the chunk size. So the chunk size 2 by 5. So what does that mean? It means we actually have 2 chunks that make up this array. Why we have 2 chunks, again, I'll come back to that in a little bit. Compute method, again, that's a NumPy ND array that's returned there, and here's where I show that that's exactly what's going on. So the methods are the same story. The methods, people at the background can be able to see that. This is our Dask array. We call a mean method on it. We get a Dask array with a mean aggregate. Called like this, we do a reduction across all axes, or all dimensions, effectively, which means we're going to get a scalar value for the mean of the whole thing. Float 64, chunk size 0 is a scalar. And if we want to know the actual value, 4.98 shouldn't be a surprise, where values go from 1 to 9, and our average over 100 values ranging from 1 to 9 is 5. Now if we were to go here, axis equals 1, axis equals 1. Think about what we'd expect to happen. Well, if you're not familiar with NumPy syntax, you might have no clue what's going to happen. Axis equals 1 means rather than reducing across all dimensions, we want to reduce across a single dimension. So we're going to reduce across columns. We're going to reduce down columns. So we're going to get the mean of each column. That's usually when we organize our data. We try to, if it's not something like a vector image or something like that, usually our rows are independent observations and our columns are independent dimensions. So if we did a mean, we would do means down columns. So axis 1 would be like a common way to do a mean. Shape 60, float 64, chunk size 20. 3 chunks. And when we compute it, we then get an array of 60. Okay? All right. I've already talked about why you should care that Dask looks like NumPy. This is really just us talking about warm you up to the idea that Dask can provide parallel versions of data structures you're already familiar with. The chunk size parameter, it's how Dask breaks up an ND array for parallel processing. Those subunits can be operated on in parallel. In a real system, would we be trying to parallelize a 60 by 60 array? No, never. We're only doing that here because we can reason about it. We can look at the whole thing if we need to. We can touch it, because Python's like a hands-on, high-touch language. So it's only for pedagogical reasons that we're dealing with this little teeny thing. Dask is interesting when you're dealing with very large data sets, when you have runtimes that are painful for you, and painful might be minutes, painful might be hours. It depends on what your pain threshold is. Painful might be your data is so big it doesn't fit in memory, and then that's immediately painful. So we're looking at small things now just to get a sense of how this stuff works. Okay. All right, I'm going to give people 5 minutes to do exercise 1.2, where again, I want you you only need 2 fingers for this, shift and enter, but I want you to think about what's happening rather than just executing it and looking at it and going, oh, wow. Think about what you expect to be returned, and then if you're surprised, that's actually a good thing. But hopefully in the process of thinking about it, and maybe not being surprised, but thinking about it, you'll get a sense of what Dask is doing internally. So there's a few guiding points in here. So you have 5 minutes to go through this, and then I'll do some narration. If anybody has any questions you'd like me to come and talk to you about individually, I'll come and talk to people individually for 5 minutes. Anybody? Did you download your data? Maybe? You don't know. Okay. Anybody? Well, still downloading. Okay. We don't need it yet, so you got a couple more minutes for it to show up, so you can do the exercise 1.2. Anybody want me to come and talk to them individually? Okay. I'll talk to individuals for a couple minutes. Exercise, and I'll narrate. All right, sorry for getting distracted on why everyone should use Conda. All right, computations on Dask array objects. So again, reminder, our A object is here. Our array object is, now, this is interesting. This, what we're looking at here, might remind you of what we saw when we did the mean operation. Our randint is actually a parallel randint that because of lazy evaluation, it hasn't been invoked yet. So our randint is effectively like a closure that's primed to execute at the latest possible moment when the results are actually required. So because of the way the randint, the parallel randint function was called, we know the size that it's going to create. We know the return type, and we told it what the chunk size was going to be. We told it the size as well. But this hasn't been executed yet. So if this were like randint 1 million by 1 million, so looking at whatever that is, a trillion element randint array with however you want to chunk it up, provided you've got a large enough distributed system. And you could definitely do that. So Dask has been run, the largest systems we're aware of that Dask has been run on about 5,000 computers. So you think about like if you've got enough money for 5,000 computers, and those computers each have 4 cores or 8 cores, because they're not going to be like laptops, they're going to be rack-mounted machines. They typically have like 4 cores, 8 cores, that kind of thing. How much memory those machines have, let's say they typically would have probably 32 or 64 gigs of RAM. So do like 5,000 times 32 or 5,000 times 64. It's like a lot of memory, right? We're talking about hundreds of terabytes of memory. So you could do an extremely large randint. You could create an extremely large distributed array of randints, and you just want to make sure that your chunk sizes, each individual chunk, like would fit in memory on each machine that you were running on. And so it could be this like really gigantic thing. And A here is just your view to that massive distributed randint where it's just waiting for the latest possible moment for all of those 5,000 instances of chunks to like be triggered and to go and actually calculate the values and populate their individual chunks with the necessary values. But it waits the latest possible moment. Okay? So here we're dealing with something which is 60 by 60. So 3,600 elements. Chunk size is 20 by 20, so like 400 elements. So what's this going to look like? What's the picture you have in your head of what this is going to look like? Hopefully everybody has the same picture in their head. Tic-tac-toe, right? Hopefully that's not just like a Canadian, North American thing. Everybody knows tic-tac-toe, right? I don't have a whiteboard here. I'd draw it for you if you're not familiar, but I think everybody's familiar. So you've got a tic-tac-toe board, 20 by 20 blocks in each one. So we've got 9 chunks in our structure here. So we're all here at EuroSciPy. Transpose of A times A. What's that going to do? Well, if you think about what that's going to do mathematically, the diagonals for our A, the diagonal chunks for our A, can perform this operation autonomously. Each diagonal element, those 3 diagonal elements, you take the transpose, multiply it by the original, and add 100 scalar to it. So those 3 bits can happen without reference to any of the other 6 blocks. The other 6 blocks, there's a little bit of interplay that goes on, but it's not like fully linked. So like in your head, you should have a mental picture. Maybe you didn't think about that when you looked at it. I was hoping you might think about that when you looked at it, but hopefully now you're all thinking about like what's going on. So we have some natural parallelization that takes place, and Dask is just going to like look after that stuff for you automatically. In fact, we're going to get to see how that happens in just a second. So only when we call compute do we actually get the results. So hopefully you guys went through all of these already. Oh, right, and I wanted to emphasize this like chunk size piece. So here we did 3 to 5, 10 to 20. Our shape was 210, and our chunk size was 210. Why does this happen? Okay, now that we're thinking tic-tac-toe boards, and we're thinking like computers all over the place, and one computer handling each one of those chunks is like a good mental model to have. And we think about where this slice lives. This slice lives in the very first chunk in our tic-tac-toe board, the top left chunk. So the chunk size is going to be 210 because that chunk is entirely inside that block. So the chunk that's like all right there. Now, when we do this, we're now going to span. And so when we span those first and second chunks, the resulting OS to create is in the first block, the second one is in the second block. Dask looks after all of that for you. But this is just so you get a sense of what it's doing for you, and also these pieces. Okay, we already looked at some of these bits, so I'm just going to go over. It may not work for you. A is this randint. So when we want to do this randint, what's the connection? What are the connections between the blocks in our chunks for a randint operation? Is there any connectivity between those blocks? There is no connectivity. There are 9 independent blocks. You can't read these, but they say apply random. And then here it says randint number 0, and this is just like a reference to the output. I'll take your question in just a second. You can't read what it says in here, but these are 0, 0, 0, 1, 0, 2, 1, 0. These are the indices of where they are in the resulting graph. Now, Dask will do this for like an ND array is an n-dimensional array. It's easy to think about things in 2 dimensions. It's hard to think about things in more than 2 dimensions. 3 dimensions we can just about handle, and beyond that it like gets really complicated. So we're only talking in 2 dimensions here. Like cube, square, it can be literally like can't be ragged, but it can be an arbitrary hyper-rectangle, I guess. We call it a hypercube, right? You'd have the indices that each one of these chunks referred to. And in our example of like our million by million across 5,000 machines, you get your chunk sizes right, and you'd have some number less than 5,000. If you've got 5,000 machines available to you, you want to make sure that your number of chunks in your overall system is smaller than the number of machines you're trying to distribute across it. And that's a problem for you to solve. Dask today won't do those parts for you. There's a question, yes? Mm-hmm. Yeah. Yeah. So you can provide a seed. You can provide a seed in the same way. Now the part that I couldn't tell you is how Dask will provide you with identical random numbers across your system, given the same seed, so you can seed it like you would normally seed it. I would be surprised if it gave as a NumPy ND array with the same seed. Okay, I don't think that would happen. But yes, it accepts a seed in the same way. And how it progresses a single seed to quality of your seed of numbers is important. But if you're implementing this operation. How do I get this so we can see? Oh, you know what? I think there's a trick here. I think I can do. Yes, there we go. So every time, this must be new. Every time you run visualize, it writes a PNG file to mydask.png on disk. And so you can then, if you can't see it in your notebook or something, you can then open it. All right, so this I can size. So it's all on the screen. Here, one independent block. Here, one independent block. Here, one independent block. Okay? These other ones that have linkage, there's an apply random, there's an apply random. And that it has to do, if you think about what has to happen when you do a transpose multiply, it actually only interacts with one other block, its transpose block and the chunking. And so that's the 2 that are linked, and then 2 that are linked, and then 2 that are linked. And so those are our other 6. So Dask is able to execute this. What are its entry points? Well, it actually does have 9 entry points, even though it looks like on the bottom there's only 6. These are nodes that have no inputs. So they are possible starting points. So we can initiate this computation 9 ways parallel, but that's not to say that you're always going to be able to make use of 9 cores. But this is like, at most, a 9 ways parallel system, given the way that it's currently been chunked. So this is meant to give you some insight into what Dask is doing automatically for you, and where you would have communication if this was actually between machines. So if these were like very large random numbers, bigger than memory, and you had 9 computers available to you with, say, 64 gigs of RAM each, you would need to do a communication step here and a communication step here. So communicate there, and there'd need to be some network traffic. Yes?
Those 3 independents, they are essentially the 3 blocks in the diagonal.
They're the diagonal. They are the diagonal, that's right. So they execute independently. They have no communication. Okay?
So,
Yep.
so does Dask implement any strategy for hiding communication latency in this graph?
I don't know if you're asking a good question that I don't know if I know the answer to. Does Dask? Yes. Okay. So I think the answer is yes, which is that Dask will maximally. It knows the task graph before it executes. So we can build this task graph. Remember, we could do. Well, I say remember. We could do b.visualize before we did b.compute. So this could be like computing. This might take an hour. Computing it 9 ways parallel then might take still 7 minutes or 5 minutes or something like that. Dask knows its task graph that it's going to execute before it executes it. It knows the path that it's going to follow. It's not doing like discovery and dynamic graph building, okay? Because it's not doing dynamic graph building, because it knows its graph before it starts execution, it is able to say, how do I maximally localize operations on the same machine? So in this case, if we had 6 machines, it would intelligently say, okay, I can use 3 of those machines for the 3 independent parts, and then 3 of them will get the linked parts. They'll each get one of the linked parts, so we don't need to communicate across machines. It will do that, okay? I think that's answering the question you're asking. Okay, let's carry on so we can have a good 30 minutes to do our part 2, which is when we'll get into actually building some stuff ourselves. Where are we in this one? Okay, so on that basis, we've actually, although we've only looked at NumPy ND arrays, and we've looked at like chunk size, and that's it, you might be thinking, I don't feel like I've learned very much about Dask. I hope actually, you know, later today, tomorrow, next week, you're going to think, oh, okay, I actually learned a lot about Dask from this one very small example, looking at a very specific data structure implemented using Dask in terms of what Dask has done. Now, before I go on to exercise 1.4, I'm going to actually go back to my dum-de-dum Dask benefits. So we've looked at this out-of-the-box parallel data structures with parallel methods. Low-level primitives that you can use to construct your own distributed data structure, and the low-level primitives that let you construct your own parallel algorithms. Dask has used those primitives to create the Dask array on top of NumPy ND arrays. It's used those to construct a Dask data frame on top of a pandas data frame. You can use those Dask primitives to construct your own distributed data structure with your own parallel algorithms, methods that operate on that distributed data structure. And you will understand what parts of what Dask this story. Dask won't figure out your task graphs for your parallel algorithm for you automatically. You will need to like construct your own graphs for figuring out how you connect distributed data sets and how you perform an operation in a parallel manner across. If in your head you've got like a workflow, which is a natural parallel task graph, you can just use, like if you're used to like MPI primitives, you can use Dask to build your own task graph. You build your own abstract task graph, and then you can seed it with data, and then you can execute it. And so if you have problems you're working on that you think, oh my gosh, I've got stuff like this that I draw in my notebook or on the whiteboard all the time, you can implement those algorithms, those like fixed algorithms, those fixed look after the dependent nodes. It's for you. You just need to basically like wire the pieces together. right? We're not going to go into depth of detail, but in the next 30 minutes. But understanding these and how connection will make you feel empowered to take your next steps. Okay, I'm going to give people less than 5 minutes, but a couple minutes to go through these operations. Here, this command here, I'll note, is a Mac and Linux only one. This is just to give you a sense of how much data is in there, and but otherwise, take an opportunity to run through those. Also, you might want to go back and run through those 1.3 ones or look at them a little bit more. But I'll give you a couple minutes to look at those. And yeah, we'll quickly finish this, and then we'll go on to the next set of parallelizing pre-existing algorithms with the Dask scheduler and Dask delayed.
As soon as I call compute, I always get the result back to my local machine. If I have my
Yes.
Yes. If I call computer early, then I might blow up my memory.
Yes. Yeah.
I don't reduce the size to something.
That's right.
Yeah.
Yeah.
The whole thing.
Yeah. You want to compute late. Dask will compute as late as possible. You want to leave things in their Dask form as long as possible. And we'll see in the next part 2 notebook, we'll build up a complicated task graph as we expand an algorithm, which is just linear algebra. So we all should have like an intuitive sense of what's going on in terms of like just the linear algebra that's happening. We'll then see the Dask task graph as it grows and grows and grows. And it's only when you press like the fire button that it executes it. And it executes in a distributed way. And then hopefully at the end, you've got something which is manageable on a single machine. But even then, maybe it doesn't need to be. Maybe then even you can live with a distributed piece and you can take chunks or pieces, perhaps. Something to think about.
Then you have to say, like, partial compute or keep it, pair this computer, or how do you do it?
I'm blanking on the name of the option. What's the thing that lets you save the, that caches the result? Okay, so Dask throws away results because it's designed to do big problems where you're like going to be memory constrained. And if it like retained references to the things that it computed as it went through the task graph, you'd like lose immediately. So it's constantly trying to like, well, not the Python garbage collector. Dask is intentionally trying to retain your points in your task graph. So it'll recompute them if you ask for them again, unless you explicitly tell Dask to like cache that piece of information or cache that node. And then when you call compute again, it doesn't actually compute to that point. It'll just return the pre-computed result. So there are ways in which you can tell it to hold on to that result so that it doesn't have to recompute it if you need to come back to it multiple times, which is part of the answer to your question, but not the full answer.
I can do slicing. So if
Yep,
I
you can do slicing.
Slicing on a not computed thing yet, it will only compute the slice.
Yes, yes, that's right. Actually, yes, that's another great point. When you do a slice and do a selection for a slice and then do a compute on that slice, it only does as much as it needs to get that result. And it'll do that automatically.
But I have to be smart to do the right slices, otherwise that maybe.
Yeah. Potentially you have to be smart. But in the worst case, it'll do the minimum amount of compute to give you that result.
Does that actually do optimization of the graph in the sense that if you have a slice operation and some computation, you can switch them around automatically using that?
I'm pretty sure it doesn't do any kind of optimization at that level. But it would be an interesting question to ask on, so Stack Overflow is the main mechanism by which the Dask team wants people to like engage with them. So if that's a question you want an answer to, post it on Stack Overflow and tag it with Dask. And they'll pick it up and somebody will answer it. They love engaging in those kinds of conversations. And if it then becomes like a feature request where you've got ideas for what, like an actual, not abstract idea, but you could actually write some code and say, Dask, I wrote code that looked like this. Dask came up with a task graph that looked like this. But if it was smart, it could have optimized it and come up with this. What can we do? What can we do to make that happen? Then that could go into GitHub. So that goes into GitHub as a feature request, as opposed because like it's not an abstract. Hey, why don't you guys do like expression optimization, which they may or may not do. That's a Stack Overflow question. But if you know the answer to what they do and you have a specific answer to what you'd like them to do, then that can go into GitHub. I think there's another question over here. Yes.
Yeah, we are using something
Yes?
How can it deal with the reproducibility of random results?
Yes. Someone asked that question 20 minutes ago. It's fine. I'll answer it again. It's an important question. It accepts seeds. It will always generate the same results with the same seeds. I have no idea how it distributes the seeds across parallel randoms. It does it somehow, so you actually have different random numbers in different places. I don't know how it does it. You could ask on Stack Overflow. Okay? All right, let's go through these and let's get to our second notebook. So pandas, so what PDF is our pandas data frame. So we're used to pandas and pandas read CSV. So we read in a single CSV file. We look at our CSV file so we get a sense of it because Python's a high-touch language. We want to look and touch our data and our code. So we get a sense of what we're looking at here. We've got 250,000 rows by 23 columns, though you guys probably can't see that down at the bottom there. 250,000 rows by 23 columns in that for that year, for 1990. So Dask data frame, DD instead of PD. We're able to do a dd.readCSV. What's different about this? Star.csv. What's that going to do behind the scenes? Hopefully I've basically told you what it's going to do behind the scenes. It's going to create a data frame for every one of our CSV files. So I haven't executed this one yet. So here we've got 2.6 million rows in total. We've got 1990 to 1999, so we've got 10 CSV files. So how many actual pandas data frames are we going to expect are going to be created? 10. What's Dask going to give us? It's going to give us a view, which is one pandas data frame, but it's a Dask data frame. So it's going to give us a synthetic view across all of those. So we're able to use a star operation there. You may need to fix slashes and paths if you're on Windows, and I see a lot of people here on Windows. So either that or do os.path.join if that's required for your system. Okay, what's our data frame? Well, Dask peeks in enough that it sure of the data. It's done type inference from the first one that it looks at, and it expects the same. Important point, because we're going to come back to that in a second. Number of partitions, there's 10 partitions in total, because there were 10 files. And it says there's 30 tasks associated with this. So it knows the number of tasks in its task graph. So there's our 10 pandas data frames. They're completely independent. Our synthetic view, there's no connections on them because there's no operations that connect. It's just the view of the task graph is every one of those is independent. Have these actually been read into memory? No, they haven't. Lazy iteration. It's peeked into the first one just to get a sense of what the data looks like. It has no clue how much data it's looking at. It just knows it's got 10 things, and they all better look the same as the first one because it's doing type in first one that a little look ahead. It actually gets it wrong, and so we're going to see in the next step how we fix that. Yes.
You said you have 10 files, but where did this 30 task come from?
Yeah. 10, 20, 30. Okay, so the task graph actually is 30 nodes in it. That's still not quite answering your question. So there's 30 nodes in the task graph, but you're saying, why are there 30 nodes? So you're still saying, why are there 30 nodes in the task graph? Because the pandas mechanism for doing this is broken up into steps. So when you do pandas, okay, step back. When you do pandas.readCSV, does it sit there and go, you didn't really mean to read CSV? So I'm just going to wait for a little while. When you execute pandas.readCSV, it's read CSV. It's going to do it. If the file's not on disk, it's going to bork out. If the data's not in a CSV format, I can't read it, it's going to throw a stack trace, right? It's going to read that file right away. What is Dask going to do? Dask is going to go, okay, I'm going to get ready to read CSV. I'm going to see how many files there are on disk. Okay, I see there's 10 files on disk. All right, I'm going to look at the first one. And the first one, I'm going to look a little bit into it so I get a sense of what this data structure is going to look like. And then it says, all right, now I'm going to set up my task graph for these operations. The first thing I'm going to do for each of these 10 operations is read block from file. I'm then going to pass that, which is going to be my file handle reader. I'm going to pass that to pandas read text, which is like an internal operation within the Dask data frame module. And then I'm going to check the metadata to make sure the thing that I've read matches the thing I'm expecting to read, because I don't want to just do, like, I could have 10 CSV files that I've read in, but they're like different CSV files. Well, Dask needs to make sure that they're compatible. So there's a point where we're going to get through this, and then we're going to make sure that those 10 things we've read in, actually the metadata is the same. That's our third row. So there's our 30, so 3 stages times 10 files, 30 nodes in the task graph. How many of them have been executed at this point? 0. Okay. All right. So now I'm just going to go and run through these because I want to get to the next part. So we've got a few minutes for the next section. Okay. So we're reading the same file. I'm reading it using os.path.join for people on Windows who they're changing slashes didn't work for you, so this will work for anybody, provided the data actually did download eventually. We can do parse dates because our dates are in each individual columns. They're not in a natural date. Like, we can't convert one column to a date time. So instead, we're going to do parse dates. And our new synthesized date dimension is going to come from 0, 1, and 2 columns, so indexed into those, which are year, month, and day. And then we're going to give a D-type hint. Well, I say hint. We basically are going to force the D-type of these three dimensions to string, float, and bool. Because if we don't do this, it actually turns out that the guesses we make from the top of our data is going to be wrong for all of our data. So here in this case, we need to actually give it a hint rather than let it infer. We look at our columns, so we can do dataframe.columns. What's the story here? We're looking at a Dask distributed data frame. We can do a columns operation like we would do on a regular pandas data frame. We can do a dot lookup of a series and get back a Dask series structure for a particular dimension. It's a Dask series. There's 10 partitions to it. What's the data that we're looking at? Flights in and out of New York City airports. So what would we, or I say in and out of. I guess it's going to be out of because I know what the results are going to be here. Flights arriving at or leaving from New York City airports. That's the right way to put it. So we can do df.origin.unique, compute. We get back, if the data sets had European airports, I would have changed this to European airport. Unfortunately, the Dask team only has this set, so I couldn't do the same thing with European airports. So just like kind of, although I'm based in New York, I was trying to actually make this a little more international, but no such luck. Newark, LaGuardia, JFK. And an operation like len of data frame. What's len of data frame going to do for us? It's going to ask every individual data frame what its length is, and then return its total length. Now, because we're calling len as a function on the data frame, it actually has to execute it, and that forces the dot compute, and that then gives us our 2.6 million. If we called the len method on the data frame, we would get back a future. We'd get back a delayed, so we get back like a delayed object. Yeah, what's your question? Yes, do you have a question?
When you do len, actually, it doesn't take advantage that it's in parallel.
This one doesn't. Well, okay, it's because it has to recompute it to figure it out. It has to reread in the data because it throws away the results. It throws away the fact that it's computed it already because it doesn't hold on to the results. The data frame does what it needs to do, and then it lets go. There's a parameter here that I'm forgetting that would allow us to have it keep those results after it does the compute, and then this would execute instantly. Okay? The last thing I wanted to do here on this was to go B and do this. So this is our task graph for doing the origin dimensions, the uniques. It will, what's happening here, if it were bigger, you'd see the structure a little bit better. It's trying to do basically like a log n aggregation of uniques across the subsets. So rather than doing uniques for each one and then a one-way merge, it's trying to do uniques across the set and then doing a log n merge rather than a merge across all uniques. So that's like just the way the data frame unique operates. And then we've just got a few other bits for data frame. I'm not going to leave these ones for you guys to run. We can do a mean on a dimension. We can figure out the arrival delay mean across all of the data. And again, this is like going to be a parallel operation. We can visualize it, the calculation. And we can do group bys. So day delay is a group by. That calculated like instantly because it didn't, I mean, it built the task graph instantly because it doesn't actually compute it. Compute takes a little bit longer, but it is in parallel. And the day of week, we're able to see the greatest delays are on Fridays. Day 1 is Mondays. Most people flying in and out of places on Fridays. And we can see that to figure out this group by operation, well, you can't see it very well, but at this point we have a sense of how these things work. Okay, so we're now going to have a few minutes, not as many minutes as I'd hoped, to open up the number 2 notebook and consolidate what we've learned so far and learn one new thing, but one very powerful new thing, which is a way in which we can wrap pre-existing code to allow Dask to build task graphs because of its ability to infer connections between parameters. Is kind of the best way to put it. Okay. So I'm going to skip kind of the like conversational part that's in here. We've got a nice picture which shows us our story about our distributed NumPy arrays. So our Dask array composes a whole bunch of NumPy and D arrays. It gives us a synthetic view over a bunch of NumPy arrays. We've gone over these operations already. The part that maybe is interesting to show here is that some even quite sophisticated operations like an SVD can be performed in a chunkwise manner. Now it's a chunkwise manner that has to like vertically chunk the data, but we've got here random numbers, 100,000 by 100,000, and we've got chunks of 100,000 by 500, so that's 200 chunks. And we're able to then do and so that's a distributed data structure. We should all now be familiar with like how that's chunked in distributed data structure. Structurally or topologically, it's like a vertical arrangement, but still 200. So we've got like 200-way parallel random numbers. We can then do an SVD on this, effectively like with 200 independent components. We can do an SVD where we do SVD on x dot x transpose, which is like a common sort of way to get your approximating effectively, if I'm remembering my linear algebra correctly, your linearization algorithms, like your eigenvectors and eigenvalues, I think is what you get out of your SVD. That's, if memory serves me correctly. If it doesn't, then whatever, and people who care about SVDs will know what it actually is doing. But it's a common operation. You get your US and V matrices out, and so that's a nice thing that Dask can just do. In fact, I say don't compute this. Turns out that I changed the numbers around in a way that you can actually run that. I think it takes like a minute or something, not too long. Dask data frames. We looked at Dask data frames. Okay, so now here's the new piece that we're going to see in our last couple of minutes here. Without doing any other work, Dask will parallelize to utilize as many cores as it sees visible on your system using a multi-threading strategy. So it won't start up independent processes. It won't go out to the network and find other Dask machines and like cooperatively, magically push code and data to other machines. It will start a multi-threaded, it'll multi-thread the execution on your laptop using as many threads as there are CPUs. So that's what it'll do if you don't tell it anything else. There's things you can do where you can like tell it what it should use for parallelization, whether it should use processes or threading, and how many threads or processes it should set up. So I'm not like getting into those details. But the distributed client here is the best way to actually make a connection to an official scheduling object. So if you start up a client that connects to a scheduler without specifying explicitly a task scheduler that's going to deal with like starting up these independent nodes in our parallel task graph as it executes, which all just like you saw, you didn't do anything magical, you didn't execute any commands, and stuff just happened. Actually, if you timed it, you would have seen a bunch of these things happen faster than they would have if you'd done them in serial. We didn't look at timing information in the first notebook, but you can trust me, or you can experiment and see for yourself that they will be faster and they will be in parallel for the right size data. It all just does it automatically. Here, if you start a client and you don't specify an explicit scheduler, it'll start a scheduler up in the background. And in this case, it'll actually start up a multi-process scheduler. And it'll then give you a reference to the client side that'll connect to that. So in my Jupyter notebook, I am driving and creating those interface components where the actual data structure and the individual workers are managed by a scheduler. And that scheduler might be like a cloud-based scheduler. It might be on the computing cluster in our research computing center. Or it might be on a really powerful like workstation that's sitting under my desk but isn't my laptop that I've got like a network connection to, whatever the case may be. Okay, so you can put in like an IP address in here and make that connection. If you don't do that, it'll start up a local scheduler on your laptop, a scheduler process, independent process, that'll then trigger independent multi-process execution, again, for the number of cores that you have on your machine. So I'll execute this, and I have hyper-threading, so it thinks I've got 8 cores. I only have 4 cores for real, 16 gigs of RAM, and the scheduler's on my local machine. So I'm going to click on that link, and we actually get like a graphical view of this, and I'm just trying to get this in a way that, whoa, that's a little too big, in a way that we can kind of sort of see this all on the same screen. All right. Status. And you're welcome to follow along with these steps. So you can like shift enter and execute these. Okay, I'm going to hope that that isn't a major problem and just carry on. And this here, I now need to pull this over and then bump my font size down. A little bit tricky getting this all on the screen, but we're going to do our best. Okay, so if I'm a little worried about what that error is going to mean for me. Okay, it's because I already have, right, I know why. It's because I need to go and do commands, restart. For you guys, this probably worked okay. For me, I think I didn't properly reset and restart my, my process here. Yeah, okay, so I restarted it and now I've now got the view that I need. Let me see. Fingers crossed. Good, no errors that time. Here, reload my status. Okay. Okay, so I've done a bunch of you're not going to be able to read these very well, but it's the same stuff we did at the end of the last one, a group by, day of week, delay.mean, but we know that doing delay.mean, it hasn't actually been executed yet. Again, we looked at that task graph before. I know that's not really readable, but that's not super important. This is the task graph that we're going to execute. I know it's very faint, but we've got the nodes at the bottom. We can start up to 10 of these in parallel. And then we get at a point where in terms of doing our group by operation, we need to sort of aggregate results. So there's a little bit of cross communication that needs to occur, and that's what you can vaguely see at the top. So what you want to notice now is that when I do this execute, if all goes well, our picture on the right-hand side, which is our status of our scheduler, should update to show a bunch of tasks executing. So that's like a visual path of the execution of those instances. And again, if we had 5,000 of these, we would have 5,000 barely visible little lines there showing the progress that we get across our cluster of systems. This is a really powerful way to see what's going on. We can actually, again, you're not going to be able to read what, but we're able to go and like mouse over these, and it gives us information about what was being executed and how long it was being executed for. This is a nice bouquet plot, so we can go and like zoom in. What's happening with those particular nodes. Remembering we've got 10, but we've only got 8 cores, so there's a little bit of doubling up here on some of the operations. And so this is showing us that execution, that task graph. Again, here, there's like 1, 2, 3, 4, 5, 6, 7, 8, and then 9 and 10 are the things that are slowing it down, because we only had.
Only because you're dealing with the task data frame and task array. You use normal NumPy array, or it's the same? Or?
Because we're looking at a Dask scheduler that can track the execution.
No, but I mean, if you are not defining task data frame, single data frame,
Yep.
the distributed part of Dask is still working, or you need to
Through a few more bits of this, I'm going to go through the whole, but I'm going to take a couple more minutes of your lunch. Besides the food, there's going to be huge lines, and so just stay sitting here for another couple minutes, okay? All right. So the story for the next few minutes that we're going to talk about is the fact that there are many problems that aren't just big arrays or big data frames. There's many problems that, as an example, again, hard to read because of the way this is set up. Let me try and bump the font size here. So we can do a Cartesian product R of A cross B, where Rij is a function of I and j. So we have our results dictionary, and we go across all A's and all B's, and then depending on some condition for a particular A-B combination, the result at a point is going to be either F or G. So whether it's F or G is individually dependent on like the details. So in kind of NumPy speak, that would be like a where operation. You'd like mask over an where and have like a projection of F under this condition and G under this condition kind of thing. So this kind of has some ways in which NumPy gives you the ability to have some succinct where language, which would let you project F under certain conditions and G under different conditions. But this concept that there are things that you want to do that don't like there's a parallel aspect to it. Every A-B pair can uniquely be identified without reference to other A-B pairs. But there's not like a built-in function that's going to let you do that. So it's parallelizable, but it's not a list or a data frame or an array. So what Dask allows you to do is utilize this delayed function wrapper. The delayed function wrapper will lazily construct the graph and say, okay, results at AB will be the delayed result of this F or this G. and say, let me just like build up all of these things that would go into figuring out the total R result matrix. And then at some later point, I'll build up that task graph, and at some later point, I will go and execute it across my 8 cores, or across my 100 cores, or across my 5,000 cores. Because the data is too big, or the computation is naturally parallel and takes a long time to run in serial mode. So if we understand this concept of function wrappers, so we wrap the function f, and the delayed as a function wrapper is a function we call on a function, and what does it return? It returns a function. And so that function that's returned here is callable, and what's it callable with? With the parameters a and b. And again, what's the concept that we're getting here? We're getting a closure of the function f with the parameters a and b. And the closure is a Dask delayed function that Dask will be able to figure out how to build it into a task graph. And Dask will be smart to figure out whether there's dependencies in the references of these A and B things, which don't have to have any Dask awareness themselves. Okay. So let's look at an exact example of this. Here we've got a function s that takes 20 milliseconds. We've got a function f, that takes 20 milliseconds, and it returns s minus t. And we've got g, which takes 30 milliseconds, and it returns s times t. These are scalar values. S and t are meant to be scalar values. Our uppercase a and b's are random integers from 1 to 10 and from 4 to 13, size 50, size 25. So they're vectors. And we can now go and we can execute this. And this here is regular f, regular g. F and g have sleep in there to simulate workload. They're there to simulate, like, it's a 20 millisecond hard computation. It's a 30 millisecond hard computation, rather than something which is trivially fast. And so if you do the math on how many A's there are and how many B's there are and the average time to execute these and how often this is the case, you will see that we're going to have something like, I think it's 1,500 executions, which for the average execution time means this takes about 30 seconds to run. So it's 30 seconds for that to run serially, because it's actually going to go through this for loop and execute every one of these F or G's for every one of the A-B pairs, depending on the relationship between A and B. At this stage, there's no Dask involved. There's no Dask. Computations that take 20 milliseconds or 30 milliseconds takes 30 seconds to do the whole execution to figure out this vector. What are the results that we get back from this? Taking a slice through the data. How many results do you expect there to be? Well, there's 81 results because we're actually building up a dictionary in the data. And now we use Dask delayed, and we create a delayed version of this, which allows us to compute these in parallel. Now, why did it take 100 milliseconds? They're delayed objects. They haven't actually been calculated yet. But we know how many results we've got. We can use this just as a little algorithm to say what our estimate for the execution time is. And now, if I bring these onto the screen at the same time and place, compute the results. We saw results execute over there. How long did it take? 372 milliseconds. That gave us 100 times speed up on the execution of that. What's important about what I just showed you? We had functions. We had nested loops. There was no Dask involved anywhere. The only thing we did was wrap a pre-existing function that did stuff, that took time, that worked on regular data, and we got 100 times speed up to compute the results. This is a capability you can leverage today in code that you've got. We have the exact same results, the exact same numbers. It's doing the same thing. We saw the computations, the executions on the right-hand side there. It is definitely lunchtime. The code that sits in here lets you go through and build out your understanding of how task graphs are created. And so you can read through these. You can do it as like a little mini tutorial to your friends and colleagues, to your family at home. I'm sure they'd love to know about Dask. You can tell them it's the future. It's so much more interesting than Spark as far as I'm concerned. You can watch these graphs be built. You can watch them become more and more sophisticated. And you can say, I understand what's going on there. I understand what Dask is doing. And then for my very last comment on restart kernel, my very last comment down here. This delayed wrapper that we showed in this last example, it was a little bit nuanced. You might not have totally followed it. We have two functions here, increment and add. Increment takes 1 second to execute. What are we simulating again? We're simulating load for teaching purposes. The idea is, 1, something we can understand, 2, something which is slow enough that we can like watch, kind of semi-watch stuff happen in human timescales, okay? So it's a function that does stuff. Our function takes 1 second to add a number, add 1 to a number. We've got a function add. It takes 2 parameters, sleeps for a second. It adds the 2 numbers together. In this code here, how many functions are called? Well, okay, 2 functions, inc and add. How many times are functions called? 3 times functions are called. How long is it going to take to execute? 3 seconds. 1 second, 1 second, 1 second. They each take a second to execute. How long will the sequence take? It'll take 3 seconds to run. Can you spot opportunities for parallelism? Increments here, generate x and y, totally independent. I didn't execute this part. Execute this. 3 seconds to run, no surprise. If you've seen decorators before and always wondered what decorators do, decorators are identical to if we had a function called increment that's a regular plain vanilla Python function, and delayed is a function wrapper, and we call delayed on increment, what does delayed return? It returns a wrapped version of that function that is a callable itself. And if we reassign the reference inc to that newly wrapped version, well, we have the same reference name to a new function object that wraps the original function object. That's all that decorators do, okay? So if you didn't know that before, you've just done the same thing as putting this line right. We now have a delayed version of this. Z. Going to be, what are we? We didn't actually look at the result. Okay, I'll know what Z is going to be. It's a delayed object. What's the graph look like for Z? Increment and add were written by your colleagues who know nothing about Dask. You've just parallelized them by putting @delayed. Or it's their code, it's your colleague's code. You don't get to touch their code. You don't get to add the decorator. In your own code, you go dinc equals delayed inc. And you imported their code, and you now have a wrapped version. And Dask has now automatically built a task graph. You didn't need to build that task graph. Dask figured out the dependencies, built that task graph, and now you've just saved yourself 1 whole second. But you get the idea. Okay, I'm sorry we ran over 10, 15 minutes. I'm not going to take group questions right now. I'll stick around here for a little while and answer questions. I'd love to talk to people more about Dask. I'd love to talk to people more about exciting data science opportunities around the world. BCG, my colleagues in Milan, Paris, and Munich in this local sphere are very directly recruiting for people right now. I'm recruiting for people in New York, Chicago, and Seattle. So I'd love to talk to you about that as well. But Dask, it's the bomb. So I would love to talk to you more about that afterwards. But for now, I'll let you go grab lunch. If you have questions, you can come up afterwards. Thank you very much. Yes.